What's going on, everybody? Well, our class for the past few weeks has been all about trigonometric identities. We've been learning them, we've been memorizing them, we've been manipulating them, we've been using them to find new ones, and today we're going to be using that knowledge towards the process of solving trigonometric equations. You're going to find that this is actually very similar to the process of solving regular equations from algebra, except now that now these expressions and equations now have trigonometric functions inside of them. So as you're solving for x here, you're going to have to take an arc sign of whatever is on the opposite side of the equation here. And you're going to find that in the process of us doing that, you're going to discover that most of, if not all of these, have not just one solution, but an infinite number of solutions. So how do we find those infinite numbers of solutions? How do we describe that once we've actually found that? That's the focus of today. And so before we do that, though, let's take some time to get ourselves centered here. I've been hearing from many of you that this is a time that's especially boring, where we're all being expected to be at home. But I'm telling you, the process of getting yourself centered, where you can empty your mind of thoughts, focus on your breathing, can you feel that your body is alive? Those kinds of things can actually make it so that life during this unusual time is not all that boring. So take some time to focus on your breathing and get yourself centered. Welcome back. Let's also spend some time getting ready by doing some additional warm-up problems here. I've got some problems for you to do here. This is some inverse trigonometric functions that I'd like for you to solve without using a calculator. This one's definitely the hardest one. I just thought I'd give you a challenge here. The arc cosecant of this crazy thing here. So take a look at this and ask yourself the question, to what extent can I simplify this a little bit by making it so that there's a square root of 3 down here and nothing up here. You can see that there was obviously a moment in which somebody had to rationalize the denominator here. If you undo that, it'll make it a little easier to see what the solution to this is. So that's a good hint. This is the arctangent, by the way. This is another way of writing arctangent, tangent -1. It's the inverse tangent, different than the cotangent. That's not the same thing as inverse tangent. So here we're trying to ask what value, what angle has a tangent of -1. And then lastly, we have some questions about the unit circle here. In what quadrants is sine negative, and in what quadrants is tangent positive? So take some time for those. Welcome back. Well, in particular, that first problem I know is rather challenging. The others should have been fairly straightforward. Let's take a look at this first one here. If I have an angle that has a cosecant of this value right in here, then let's actually simplify this a little bit just to get closer to the answer here. This is obviously an instance in which we had to rationalize the denominator here. So another way of writing this would have been the arc cosecant of negative 2 over square root of 3. And if an angle has a cosecant value of this, then it's going to have a sine value of this. Well, now it becomes a lot more straightforward as to which angle this is. This is an angle that has in quadrant 1 has a sine value of square root of 3 over 2, and as it turns out, that's an angle of 60 degrees or pi over 3. And the fact that it's negative, and arc sine is defined specifically on this interval, so it's always on the right hemisphere here, and it's specifically in quadrants 1 and 4. So the answer here, when this is negative, is that this is not positive pi over 3, but negative pi over 3. In the same way here, tangent is negative, and tangent's also defined on this same interval here. In quadrant 1, a tangent of 1 would be simply equal to pi over 4, but the fact that this is negative means that this is now negative pi over 4. Sine is all about the y direction here, and so where is sine negative? It's where the y direction is negative, quadrants 3 and 4. And lastly, where is tangent positive? Well, it's where the x and y coordinates are either both positive, as in quadrants 1, or both negative, as in quadrants 2. All right, so let's talk about how we start to solve some of these trigonometric equations here. Let's take a look here. The first thing that you always want to do is to get the trig function by itself. And so that's going to involve solving this for sine of x. All right, so sine of x is equal to 1/2. We'd start thinking in terms of, okay, in quadrant 1, that is pi over 6, or 30 degrees. It's also positive in quadrant 2, and so that would have a reference angle still of 30 degrees. So that would be 5 pi over 6. Here's another way of seeing it as well here. If we plot sine of x in this familiar pattern here, here's 0. This is in radians along this axis here, and we're going here, of course, from -1 to +1. And we start off here. Here's our familiar 30 degrees right here. And as we go through pi over 2 and come back down here to pi, we have 5 pi over 6 here as well, where this value of sine x touches base at y equals 1/2. So these are places where sine of x is equal to 1/2. It's the places where these things intersect. But as you can see from all these points here, this isn't the only place where these two things intersect. And so we have to account for all the other circulations around the unit circle here. And so in addition to x is equal to pi over 6 and x is equal to 5 pi over 6, the period of the sine function is 2 pi. And so we can add 2 pi to this here. And so we have another instance of a solution here at pi over 6 plus 2 pi, as well as another solution over here at 5 pi over 6 plus 2 pi. And we don't have to just go in the positive direction. We can also go in the negative direction here. X is equal to pi over 6 over 2 pi, minus 2 pi, as well as x is equal to 5 pi over 6 minus 2 pi. And there's even another instance here that you can see on the screen here. X is equal to 5 pi over 6 minus 4 pi. So you can see here that there's an infinite number of solutions that are visible here when you plot these two things together. We also know this from remembering our unit circles. So again, the period of the sine function is 2 pi, and so what's a way in which we can represent all of these red solutions here together? Well, they all have a pi over 6 in them, and then there's some multiple of 2 pi that's included here. Here's nothing. Here's 2 pi. The next one's going to be 4 pi and 6 pi. This one over here is negative 2 pi. The next one after that's before that's going to be negative 4 pi. So this is pi over 6 times some positive or negative multiple of 2 pi. So think about what it is for the green ones. Well, they all have a 5 pi over 6 in them, and here we're adding some positive or negative multiple of 2 pi to that solution. So it's the same idea here. So how do we describe this mathematically? To some extent, we've already done this in class. We describe this by adding multiples of 2 pi to n pi, to n pi. Here they are right here. So n is some integer. Z means it's an integer. It's a positive or negative whole number. And so here's how we would write that. N is x is equal to pi over 6 plus 2n pi, and there's these other set of solutions here as well, 5 pi over 6 plus 2n pi there as well, where n is an element of the set of all integers. That's literally what this says here. N is an element, in other words, a member of the set of all integers. All right, so here's some important things to keep in mind here. It's common to have an infinite number of solutions where multiples of 2 pi are added using n. Just keep in mind also, some of these functions have a period of pi. Remember, tangent doesn't have a period of 2 pi, it has a period of pi, and so you'll be adding positive or negative multiples of pi, not 2 pi for that. But for sine and cosine, it'll be multiples of 2 pi, and you'll do that using n, where n is any integer, any positive or negative whole number. And again, the way we say this is that n is an element, that's what this symbol means, of the set of all integers. So it's a member of the club of all integers here. Kitty. Okay, this is my cat Simba who wants some attention here. Okay, let's see if I can multitask here. In addition to this, a good strategy is to first find all the solutions on the interval 0 to pi, or if you're working with tangent, find the solutions on all the solutions on the interval negative pi over 2 to pi over 2, and then extend those solutions to the entire interval from negative infinity to positive infinity, just like what we did. And then when solving trigonometric equations, you should, whenever possible, write your answers as exact values. Use the pi over 6 a way of describing these things, and square root of 2 over 2 and stuff like that, instead of describing them as decimals on the calculator. This allows for us to just be more precise. But sometimes that's not possible, and you have to describe them as decimals then. So let's start by solving our first trigonometric equation here. Sine x plus the square root of 2 is equal to negative sine of x. So here, the process I'm going to do here is to get all the signs on the same side here. So now we have 2 sine of x plus the square root of 2 is equal to 0. And now I'm going to see about getting this radical on the other side over here. 2 sine of x is equal to the negative square root of 2. And now I want to get sine completely by itself by dividing both sides by 2. And so now I have sine of x is equal to negative radical 2 over 2. Well, where is that true for sine of x? If we were looking specifically in quadrant 1, square root of 2 over 2 for sine, that would be 45 degrees, or pi over 4. This is negative now, so we're looking probably at a couple of solutions in the southern hemisphere here now. The reference angle, like I said, is pi over 4. Sine x is negative in quadrants 3 and 4, and so we're looking really at 5 pi over 4, that's pi plus another pi over 4, and 7 pi over 4, that's 2 pi minus another pi over 4, that's 7 pi over 4. And the period of the sine function is 2 pi, and so the solutions on the interval that we have so far are this and this, but to find the solutions on the interval, we have to add plus and minus multiples of 2 pi here. So we have 2 sets of solutions here, 5 pi over 4 plus 2n pi, and 7 pi over 4 plus 2n pi as well, where n is a member of the set of all integers. All right, so try this one by yourself here. This will be very similar to what we did before. Take some time for that. Welcome back. Well, this problem was very similar to the one previous to it, except that we are now taking a look at values of sine that are in the positive y direction in the northern hemisphere sort of portion of the unit circle here. So the solutions on the interval 0 to pi is pi over 4 and 3 pi over 4. That was different than before. It was 5 pi over 4 and 7 pi over 4. But just like before, we are having to add multiples of 2 pi plus or minus, where n is equal to a value of the set of all integers. Okay, let's just try an additional one here. This one is slightly more complex, but the procedure is really the same, in which we're getting the trig function by itself. So we start off with this, and we add 1 to both sides here, so we have tangent squared x is equal to 1. Then divide both sides by 3, so we have tangent squared of x is equal to 1/3. And now if I take the square root of both sides here, I get tangent of x is equal to plus or minus 1 over the square root of 3 here, which if I rationalize the denominator, I can get plus or minus radical 3 over 3. Okay, so what are the values for which that's true here? Well, the reference angle here is pi over 6 that we're going to be working with here. And as it turns out, since tangent here can be both positive or negative, there really isn't any quadrant restriction that exists for the solutions here. We can be in any one of the 4 quadrants. And so these are the 4 possible solutions here. Negative 5 pi over 6, that's if it's in the quadrant 3. Negative pi over 6, that's if it's in quadrant 4. This is quadrant 1, this is quadrant 2. The period of the tangent function is just pi, and so the solutions on the interval negative pi over 2 and positive pi over 2 is just plus or minus pi over 6. And so the solutions on the interval here is pi over 6, or 5 pi over 6 plus n pi, where n is equal to z. So you could describe it this way, or you could describe it, I think it's probably better to do this on the interval 0 pi, in which case we have our 2 solutions of pi over 6 and 5 pi over 6. So we could describe it using that way, and then it becomes pretty straightforward how we did this here. We could also use negative pi over 6 and positive pi over 6, in which case we could just say plus or minus pi over 6 plus n pi. And it's not 2n pi here because the period of the tangent function is just pi, not 2 pi. So that's another way in which you could describe it. We just have to make sure that we get all of the solutions on one portion, half of the unit circle, so to speak. Since the period is pi, just doing half of the unit circle is sufficient there to get all the possible answers here. Okay, so take some time to do this one here as well. This one will be the same kind of thing where you're getting the sine of x by itself and then discovering what values of x give us those values of sine. Take some time for that. Welcome back. Well, you probably noticed that the most challenging part of this problem is the very, very end, in which we're doing a translation to simplify an infinite number of solutions into just a couple of categories instead of 4 different categories here. Hopefully everything else was fairly straightforward here, where we're getting sine squared by itself and then just sine by itself. The reference angle here is pi over 3. There's no quadrant restriction, so we have 4 solutions here, with the period of the sine function being 2 pi. We have our solutions on the interval negative infinity to positive infinity being each one of these things that are multiples of 2n pi. And so here's what I want you to see here. Let's see, if I want to plot these things up on a unit circle here. See, the first one's going to be pi over 3 here. The second one's going to be 2 pi over 3. 3 pi over 3 would just be over here, but 4 pi over 3 is going to be, sorry, this one right here. And then 5 pi over 3 is right here. And of course 6 pi over 3 is back home over here. And so it's true that we'll add 2 pi to each one of these revolutions, but hopefully we can see that another way to say that is to just count 2 of them and then to just add pi each time. Here's what I mean. If I've got, let's see, how would I put this? Let's try 1 and let's try 4 pi over 3. That's represented here with n being equal to 0. Actually, with n being equal to 1. Nope, that's wrong. That's actually represented here with n being equal to 0. And it's also represented here with n being equal to 1. So n being equal to 0 here, we have 4 pi over 3, but it's also covered by this here with n being equal to 1. So 3 pi over 3 plus 1 more pi over 3, we can get 4 pi over 3 out of this. We can also take a look at 5 pi over 3, and we can represent that here with n being 0. We can also represent that here with n being equal to 1. 7 pi over 3, let's just keep going. That can be represented here with n being equal to 2. 2 pi is 6 pi over 3, plus another pi over 3 here is 7 pi over 3. But it can also be represented here, actually here, with n being equal to 1. So this is 2 pi, which is 6 pi over 3, plus another pi over 3 being 7 pi over 3 here. So the fact that this shows itself both on the top and on the bottom really shows that the period of this repetition here isn't 2 pi, it's just pi. And that's where we get this summarization here in going from here to here. All right, so let's try another one here that we can also use. You're actually going to find that with this one, you're going to get 2 possible solutions here as we solve this out. So let's first of all write the equation as it starts off here, and let's get everything on one side and so that we have 0 on the other side. And let's notice that we can factor out a cotangent x out of both terms when we do that, leaving behind cosine squared x minus 2. All right, so we have the zero product theorem here that says that if you've got 2 things multiplied with each other to give you a product of 0, that can only happen when either this thing is 0 or this thing is 0. So we have 2 possibilities here, one that cotangent of x is equal to 0, and the other is that cosine squared x minus 2 equals 0. Let's first of all take a look at this instance here. Cotangent of being 0, that's a reference angle with pi over 2. So that happens at 90 degrees. Let's come back here to cosine squared x minus 2, and let's see if we can solve that for x. That's going to be the cosine of x is equal to the square root of 2 if we solve that. Now think about this. What is the range of cosine? It usually bobs up and down between two numbers. It's just -1 and 1, isn't it? So -1 and 1, there's no place in which cosine ever gets this big. Square root of 2 is like 1.414 and so on. So it never gets this large, so this one actually has no solution to it whatsoever. There's no instance in which this factor here will ever be 0. So that leaves behind just this possibility here, where cotangent of x is equal to 0. That gives us a reference angle of pi over 2. The period of the cotangent function, much like the tangent function, is just pi. And so the solutions, even though the solutions here on the interval 0, pi are just pi over 2, the solutions on the full interval is pi over 2 plus n pi, where n is an integer. Oh, there we go. All right, so take some time on this one here to solve this very similar problem here. You're going to most likely get everything on one side of the equation and factor things out so that you'll have two possible venues to investigate. Take some time for that. Welcome back. Well, this affords me perhaps an opportunity to explain a little bit better the process of simplifying some of these infinite series descriptions here a bit. So let me actually show you what was going on there. Hopefully this was straightforward, where you factored out a sine x and solved two separate equations here. There's no place where sine of x is going to be equal to 2, so there's no solution there. There's actually, this is called the null set, so it's a set with nothing in it, so there's no solutions to this. So the reference angle that we're dealing with here for sine x is just 0, and the period of the sine function is 2 pi, and so the solutions on this interval, the full distance around the circle is 0 and pi. And so for the solutions on the full interval from negative infinity to positive infinity, we would add 2 pi to each one of these things. But here's the thing that I want you to see as we're doing this. What are the different solutions that we have when we're doing this? Let me actually plot these out here on the unit circle. The first solution we have is 0. It's 0 right here. Boy, I'm doing terrible with this pen. The second solution we have is just pi. The next solution we're going to get is, we were coming around the circle completely here, that's 2 pi. Next solution we're going to get is going to be 3 pi. Next solution we're going to get is 4 pi, and then 5 pi, and so on. And so what I want you to see is that even though we're presenting this as having a period of a cyclical period of 2 pi, it actually repeats every pi, doesn't it? 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. And so an easier, more simplistic way of describing this would be simply to say that this is n pi, just some multiple of pi where n is an integer. So sometimes as you're describing these things, sometimes you're going to get patterns that are actually a bit more, a slightly smaller period than what you were thinking of before here. Let's actually go back to the previous problem here, where we were looking at this. So if we list all of the solutions on this unit circle here, it's pi over 3, 2 pi over 3, then 4 pi over 3, and 5 pi over 3. The next one's going to be 7 pi over 3, and then 9 pi over 3, and then so on. And is there any way in which we can describe that a little bit more succinctly? And the answer is yes. So if we go pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3, and then 7 pi over 3, 9 pi over 3, and then let's see, let's just do 2 more here, so that'll be 11 pi over 3, and then 12 pi over 3. Nope, that's not right. It's 7 pi over 3, 8 pi over 3, 10 pi over 3, and 11 pi over 3. Okay, so you can see that there's a jump here in 6 pi from this one to the next one. But you can also see perhaps that there's a jump in 3 pi from here to here, and from here to here, and a jump, 3 pi over 3. From here to here, from here to here, and from here to here. So there's actually, the period here that we're dealing with this set of solutions here, is just pi instead of 2 pi. So we can actually simplify this to pi over 3 and 2 pi over 3 plus singular multiples of pi, not 2 pi. So it helps to be able here to list out the complete series here, and to ask yourself the question, is there a more succinct way that I can describe this? You can see the jump here was in 6 pi over 3, 6 pi over 3, and so on, 6 pi over 3 here, but you can also describe this as a jump in 3 pi over 3 here, here, here. So 3 pi over 3 is just pi, and so you can see the cyclical pattern here just involves adding or subtracting multiples of 1 pi, not 2 pi. Okay, so let's keep going here. We've got some equations that are a little bit more complex here now, and we have to kind of think of this in terms of solving a quadratic equation here, where if we had an equation that looked like this, we'd almost think of this as being like, if we replace sine of x with a z, this would be like solving 2z squared minus z minus 1 equals 0. Make sure that you see that there. If I replace sine of x with a z, then I have a more familiar looking equation here, don't I? And for solving this kind of an equation here, I would be factoring this out here, and I'd be asking myself the question, what two numbers multiply to give us -2, but add to give us -1? And the answer is -2 and +1. And so, oops, I'm going to skip this. I'm going to split this up, 2z squared minus 2z plus z minus 1, and I'll do some factoring by grouping here. 2z, this first part here will be z minus 1, and then I will put these in parentheses here, z minus 1, and now I can factor out a z minus 1 from these two terms, and I get 2z plus 1 times z minus 1. All right, so, and then setting this equal to 0, I'll be able to solve for z in those two cases here. So we're going to see something similar to this as we're going through this here. Oh, sorry. Well, we're setting this, suffice it to say, we're setting everything equal to 0 here, and then we're doing this factoring like I just mentioned before here. This is 2z plus 1, 2 sine x plus 1, z minus 1 being sine x minus 1, and now we're splitting it into two possibilities here. Remember the zero product theorem, either this is 0 or this is 0. So for this one, 2 sine x plus 1 equals 0. That means sine x is going to be equal to -1/2, so we'll consider that solution here. The reference angle, we're going to coming back home to the first quadrant, we're dealing with just pi over 6 for that. We'll come back to that in just a bit. The other possibility is that sine of x is equal to 1, and that's happening at the reference angle of pi over 2 or 90 degrees. So there's some solutions on the interval 0 to pi here of the following. We've got pi over 2, also 3 pi over 2 here. It looks like I should have included that as well. Pi over 6 is one here. Oh my goodness, this is right. This is negative, and so we're going to be in the southern hemisphere for these two here. So pi over 2, oh sorry, for a reference angle here of the reference angle here is pi over 2. Let me back up. Sine is positive here, and so we know this is pi over 2, not 3 pi over 2, so that's one possibility here. The reference angle here is pi over 6, but we know that sine is negative, so that means it's in quadrants 3 or 4, so that's going to be 7 pi over 6 or 11 pi over 6. So those are the solutions on the home interval that we're dealing with here first. And fortunately, that's all we're being asked to do here, is to solve on this interval 0 to pi. So we have those three solutions there. All right, so take some time for this one here. Again, you're solving it only on the interval 0 to 2 pi, so you're not going to have an infinite number of solutions here. You're just going to have a finite number of solutions taken from solving what really, ultimately, is a quadratic equation. So take some time for that. Welcome back. Well, the hardest part of this problem probably was in solving the quadratic equation here and getting these two factors of 2 sine x minus 1 times sine x minus 1. We could probably go through that together here as we describe it in terms not of sine of x, but as of z. We could describe this as 2z squared minus 3z. I was looking at x and I said z, plus 1 is equal to 0. And for this one, we want to find two numbers that multiply to give us 2 and which add to give us negative 3. And so the only answer to that that's possible is negative 1 and negative 2. And so this allows for us here to split this middle term here, the negative 3z, into negative 2z and negative 1z. So let's just do that here. 2z squared minus 2z minus z plus 1. And here, what can I factor out of these first two terms? It's going to be 2z times z minus 1. And here, if I factor out a negative 1 here out of these two terms, I'm going to get a z minus 1 again, which means that if I combine everything together here, factoring out a z minus 1, what I'm going to have left here is 2z minus 1, which is what we have here. So if you need to do this extra work in order to be able to get to this point, that's fine. Once we get to this point, that's pretty straightforward here. We have a reference angle of pi over 6 and a reference angle of pi over 2. Sine is positive here, and so that's quadrants 1 and 2. So here's the solution for quadrant 1. Here's the solution for quadrant 2. For a reference angle here of pi over 2, there's only one place in the unit circle where that's true, and that's just pi over 2. Okay, let's just keep going here on some of these new ones. 2 sine squared of x plus 3 cosine of x minus 3. What's new about this one? Well, now we're dealing with two separate trig functions at the same time here. So one of the challenges here is for us to be able to convert one of these trig functions into another here. And so how are we going to do that? Well, when I take a look at sine squared x, I can think in terms of Efron's theorem and convert sine squared into 1 minus cosine squared here. So 2 times 1 minus cosine squared theta, that's x, plus 3 cosine x minus 3. Now when I distribute the 2 out here, I'm just going to have everything in terms of cosine squared x. I'm going to have just one trigonometric function to work with here. So yeah, that's one of our Pythagorean identities here that we're working with, sine squared being equal to 1 minus cosine squared. And if we distribute the 2, that's what we get here. And if I combine the 2 with the negative 3, I'm going to get a negative 1 here. And I have a minus 2 cosine squared x plus 3 cosine x minus 1. I can factor out a negative sign here. That's okay. That'll switch these signs here. And then I can factor what's inside here into 2 cosine x minus 1 times cosine x minus 1. Let's actually go through that process of doing that as well here. Let's do it in terms of z. So 2z squared minus 3z plus 1. Well, this is exactly the same problem we did beforehand here. So finding two numbers that multiply to give us, in this case, positive 2, but add to give us negative 3. In this case, that's negative 2 and negative 1 here. 2z squared minus 2z minus 1z plus 1. We factor out a 2z here, and we get z minus 1, and factor out a negative sign here, and we get another z minus 1. So if we factor out a z minus 1 from both of these terms, what's left over? All we have is 2z minus 1. So that's here. So let's keep going with this. We have two things to solve, either one of which can be set equal to 0. Cosine x is equal to 1/2. So that's a reference angle of pi over 3. Cosine of x is equal to 1. So that's a reference angle of 0. So the solutions on the interval, there's only one place where the reference angle, where cosine is equal to 0 on the interval 0 to pi, not including 2 pi, and that's here at 0. For the reference angle of pi over 3 here, there are two places on the unit circle where this is equal, where this is positive. One is here, and you know what? Since this is on 0, 2 pi, I really shouldn't have something negative in here, should I? So this should actually be 5 pi over 3. So that angle is coterminal with this one here, but it's within the range of 0 to 2 pi. And so solutions on the full interval here, I'm going to have to make this change here as well. This is kind of interesting in that 0 plus 2n pi is just 2n pi, and the same thing here, plus or minus pi over 3. Here it's actually a little easier to make use of the pi over 3 with a plus and with a minus. It's a little more succinct that way. Plus 2n pi, where n is an integer. All right, so take some time for this one here. Here we've got secant squared and tangent squared. Seem to remember a relationship between those two things. Take some time for that. Welcome back. Well, I wanted to kind of show you in sort of an intimate way the ways in which these things can be simplified. I wanted you to see the thought process that at least I go through when I'm trying to do this. So we have 3 tangent squared x minus 2 tangent squared x minus 1 is equal to 0. Sometimes these quadratic equations are really straightforward to solve here. Tangent squared x minus 1 is equal to 0, so tangent squared x is equal to 1. This was an important part right here, so that means when you take the square root of both sides, the answer to tangent of x could be either plus or minus 1. We still have a reference angle here in the first quadrant of pi over 4, since this value is 1, but since this can be either positive or negative, we don't have any quadrant restriction on it. We know the period of tangent is pi, and so the solutions that we've found so far here on negative pi over 2 to positive pi over 2 is plus or minus pi over 4. And so the solutions to minus infinity to plus infinity would be to just add n pi to both of those things. But can we state it more simply? So the solutions to this first one here, actually the one farthest to the right here, is pi over 4 plus another n pi. So let's say n is 1, so that's another 4 pi over 4, so that's going to be a total of 5 pi over 4. If we make n is equal to 2, that's going to be 8 pi over 4 plus another pi over 4. That's going to be 9 pi over 4. So that's how that sequence is working here. Let's see how this sequence is working. Negative pi over 4 is the first term here. And if we add another 4 pi over 4, we're going to get 3 pi over 4. If we add another 2 pi here, that'll be 8 pi over 4 minus pi over 4, that'll be 7 pi over 4. So when we combine these things together, we get a series that's pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, 9 pi over 4, and so on. So the jump is actually just 2 pi over 4, or just half of a pi. So it's actually just half a pi that it's being jumped here. And we get a little bit of a clue here that we have to have an odd number up here. This can't be an even number. It has to be 1, 3, 5, 7, 9, or so on. And so how do we show an odd number? We show it by saying 2n plus 1 in parentheses times pi over 4, where n is just an integer. So that's kind of a fun one, where you get to basically lay out what the infinite series is. And sometimes when you've had multiple infinite series, sometimes you can see ways in which you can combine them together into one that's more simply stated. All right, here's something else that comes up when we're trying to work with quadratic forms of these things here. When we're squaring both sides. Let's take this equation here, very simple, x plus 5 is equal to 0, so you know the solution to this is negative 5. But if I square both sides of this, I get x squared is equal to 25, and then if I take the square root of both sides of this, I get plus or minus the square root of 25 here, which is plus or minus 5. So as you can see here, I've actually added an additional solution to this equation just by going through the process of squaring and then taking the square root here. So this is just the thing to keep in mind here, is that when you're solving something that requires you to do a square root, it's a good idea to take each one of your solutions at the end here and run them as a check to the solution, to your original equation here. So we plug these values of x back in here, and we discover that, yeah, negative 5 works as a solution, but positive 5 does not. So that's the extra step we've got to remember here when we're squaring both sides of an equation, that we have to test both of our solutions here. And here's an example in which we're going to need to do that. So let's find all the solutions of x here on this interval here, and I'm going to first try to make all of the trigonometric functions the same one by squaring both sides here, and this will get me to a 1 minus cosine squared here. But notice I've squared both sides here, so that's a hint that I'm going to have to check all my solutions when I'm done. If I square this, I get cosine squared x plus 2 cosine x plus 1, and this, through the trigonometric identity, gives us 1 minus cosine squared x. So let's get everything on one side here and set it equal to 0, and then let's factor. 2 cosine of x times cosine x plus 1 is equal to 0. That gives us two sets of solutions here. 2 cosine x equals 0, and this cosine x plus 1 equals 0. So our first solution here is cosine of x is equal to 0. The second one is cosine of x is equal to negative 1. So the solutions here to check on the interval 0 to pi here, where is cosine equal to 0? Well, the answer is that that happens at two places. One is at pi, and the other is at 3 pi over 2. And where is cosine equal to negative 1? There's only one place on the unit circle where that happens, and that's just pi. So we have three places to check here as solutions to this equation. So let's first of all check the first one here. So if I plug in pi over 2 for x, I get cosine pi over 2 plus 1 equals sine pi over 2, and that turns out to be 0 plus 1 equals 1. All right, so that works. Let's do the middle one here, pi. Cosine pi plus 1 equals sine pi. That's negative 1 plus 1 equals 0, so that one works. Lastly here, let's take a look at cosine of 3 pi over 2 plus 1 is equal to sine of 3 pi over 2. That's going to be 0 plus 1 equals negative 1. That is not true, so the solutions that we have on this interval are just these two. Oh, gosh. Not those two. Those two. All right, whoops. You didn't even see it because I was in the way here. Yeah, so these two are the solutions to this equation on this interval here, pi over 2 and pi. Okay, so take some time to do this one here. This one will be pretty similar. Whoops. So very, very similar to the previous one, in which you'll most likely be squaring both sides to make it so you get the same trigonometric function, and you'll be needing to check all of your solutions as a result of that. Take some time for that. Welcome back. Well, you can see I fumbled a little bit at the end there, but I think I got things corrected on the final answer there. So if we take a look, we had to square both sides at the beginning and convert cosine squared to 1 minus sine squared. We then got everything set equal to 0 and did some factoring. We got two solutions for sine of x, 0 and -1. The places where sine x equals 0 is 0 and pi. The place where sine of x is equal to -1, there's only one place where that happens, and that's 3 pi over 2. So then we tried each one of these solutions in the original equation here, sine x plus 1 equals cosine. We found that 0 worked and that 3 pi over 2 worked, but pi did not. So pi was excluded near the end, leaving behind just 0 and 3 pi over 2. All right, so let's talk about this kind of problem here. The only difference here is that I've got not cosine of x or cosine of t, but cosine of 3t. So there's a little bit of just an extra step that you have to do here at the end in order to fully solve for t. Let's just start off. It's going to be very similar to what we did before here. We're going to get cosine of 3t by itself. That's going to be cosine of 3t equals to 1/2. And so then whatever this angle is in here is going to be equal to pi over 3 or 5 pi over 3. Where is cosine positive? It's going to be in quadrants 1 or 2, so that's pi over 3 or 5 pi over 3. And the period of cosine is 2 pi, so we're going to be adding 2n pi to each one of those. But wait, that's actually not equal to t, that's equal to 3t. So we have to divide both sides by 3 in both cases here. So our final answer here for t is pi over 9 plus 2n pi over 3, or 5 pi over 9 plus 2n pi over 3. All right, so take some time on this very similar problem to the exact same thing, essentially. Take some time for that. Welcome back. Well, this is a pretty similar problem to the one that we did just before here, and so hopefully this is fairly straightforward. You solved the equation here for sine of 2t and got square root of 3 over 2, and so that corresponds to an angle of 60 degrees, or pi over 3, but it's not x being equal to pi over 3, it's not t being equal to pi over 3, it's 2t being equal to pi over 3 plus 2n pi. The period of the sine function is 2n there, and we've got two possibilities here. We've got two places where sine is positive, that's quadrant 1 and quadrant 2, and so this could either be pi over 3 plus 2n pi, or 2 pi over 3 plus 2n pi. And then we just have the extra step here of dividing both sides by 2, where t becomes pi over 6 plus n pi, or t becomes pi over 3 plus n pi. Okay, so let's take a look at this kind of thing here as well. I'm guessing that you can see that when we get tangent of x over 2 by itself and we solve, we find out what angles are appropriate. We're not going to be dividing both sides by something, we're going to be multiplying both sides by something. And so we can see here that when we solve this for tangent of x over 2, we're first getting -3 on the other side there, then dividing both sides by 3, so we get tangent is equal to -1. And so where does that happen? That happens in quadrants 2 and 4. So even though we have just a single but if we're solving it on the home range of tangent, that's negative pi over 2 to positive pi over 2, then that's specifically, or if we're choosing a different home range of 0 to pi, that would just be 3 pi over 4. So 3 pi over 4 is the angle that has a tangent of -1 here. And so we're going to add n pi to this, since the period of tangent is just pi. And here's where our extra step comes in, where we're multiplying both sides by 2, and we get x is equal to 3 pi over 2 plus 2n pi. Alright, so very similar problem. Take some time for this. Welcome back. Well, this was a pretty straightforward problem. If you followed what we were doing on the previous problem here, we're solving for tangent being equal to 1 here. And I think one thing I should make more clear here is that since we're dealing with a function here that has a period of only pi, not 2 pi, what I've really been trying to say is that we only have to consider half of the unit circle, whether we're choosing 0 to pi or negative pi over 2 to pi over 2, whichever part that we're choosing there, but we just need to choose half of it in some way, shape, or form. And in that case, we have just one possible solution here where tangent is positive, and that's just easiest to use the one for quadrant 1. and that is pi over 4. So pi over 4 plus n pi is going to be equal, in this case, to x over 2. And if we multiply both sides by 2, then we get our final answer here for x. All right, here's another example of some kinds of things that we can solve here. Secant squared of x, that's got a pretty strong and a pretty easy to remember connection to tangent squared of x, so it's not too difficult to get all of this in terms of the same trig function here. Tangent squared x minus 2 tangent x minus 3 is equal to 0. So we've set everything equal to 0 here, and we've got basically a quadratic equation here in tangent. So the way that this can factor itself out is in this way. Maybe I can take a moment here to do that process here. This would be z squared minus 2z minus 3. That's if z is equal to tangent of x here. So I'm putting it in this form, z squared minus 2z minus 3. And so we're finding two numbers that multiply to give us negative 3. And add to give us negative 2. And of course the answer to that is negative 3 and positive 1. So that means I can split this up here, z squared plus z minus 3z minus 3. And if I just factor the greatest common factor out of these first two terms here, I get z times z plus 1. And if I do the same thing for these terms here, I get minus 3 times z plus 1 here. Now these two things have a common factor here as well, which I can factor out, z plus 1, and this becomes z minus 3 over here. So that's where this comes from. From here we can split this up into two possibilities. Tangent of x minus 3 is equal to 0, or tangent of x plus 1 is equal to 0. So tangent of x is either equal to 3 or equal to negative 1. And the function arctangent, remember, it's got a period of pi, and so let's just consider it on this particular interval here. And so in this case, there isn't a specific like pi over something or square root of 2 blah 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 answer here for the arctangent of 3. So let's just call it arctangent of 3 here. It's a number, it's a decimal, you could find it on your calculator, and we'll just add n pi to that. For the tangent being negative 1, that's going to be a negative pi over 4, and yeah, we'll just add n pi to that as well. All right, so try your luck with this one here as well. This is going to be a pretty similar kind of problem. Take some time for this. Welcome back. Well, perhaps the big change that we've made for this last few slides here is being able to recognize that some values of arctangent don't have clear, straightforward answers like pi over something or 2 pi over something. And so sometimes we can just leave them in this form here, arctangent of 3/4. We can find it out on the calculator and list it as a decimal. That's fine. But we can also, it's totally fine to just leave it like this here as well. Arctangent of 3/4 plus n pi, that's coming from one of the factors that we got when we factored out this quadratic equation in tangent, setting both factors equal to 0. The other factor was tangent of x is equal to -2 here, and that was our other set of solutions as well. Okay, so just to summarize all that we've gone through here, do you know how to, first of all, use algebra to solve trigonometric equations? Getting the trig function by itself on one side of the equation, setting things equal to 0, that comes in handy when you're solving it of a quadratic type because you want to set things equal to 0 and then factor. We also run into issues when we're doing a quadratic form of a trigonometric equation, and that is that if we square both sides, then once we find our solution, we're going to have to test all of those solutions with the original equation to make sure they all still work. And then third, near the end, we did some trigonometric equations that involved like not tangent of t, but tangent of 3t, where after we solved the trigonometric part, we just had to divide both sides by 3 in order to get our final answer. And then lastly, sometimes we recognize that arctangent, arcsine, arccosine, some of these inverse trigonometric functions sometimes don't have exact answers that we can write as pi over something or whatever. And as a result there, we can just leave it as arctangent plus 2 pi n in its final form there. So this is a lot that we've covered. We have been solving trigonometric equations on both the interval of 0 to pi as well as the interval of -infinity to +infinity, and have gone through the process of applying a finite number of solutions to an infinite number of solutions. This is a lot of stuff, so make sure that you're following up in class, doing the homework, and I will see you in class.